Hello and welcome to our today's webinar about the optimization of race cars by using cloud-based CFD in collaboration with Racecar Engineering. My name is Milad. I'm the product marketing manager at SimScale, and it's a big pleasure for me to welcome so many people who are interested to learn more about cloud-based CFD and how it can be used to optimize race cars and its components. As I mentioned, my name is Milad. I have more than 10 years of professional experience with engineering simulation. I also worked for several years as in the motorsports as a CFD engineer. And today, for the last 4 years, I'm working at SimScale as a product marketing manager. And as a part of this role, I'm organizing on a regular basis workshops and webinars which are introducing new users to the world of simulation. And since this is a collaboration with Racecar Engineering, I'm also very happy that Gemma Hatton is today with me. She will be also staying with us until the end of the session and take part at the Q&A. However, I would like to give the word to Gemma.
Hello everyone. Thank you for joining us. As Milad said, I'm Deputy Editor of Racecar Engineering magazine. I've studied engineering, mechanical engineering, and done a master's in motorsport engineering. And since then, I've worked in F1 as a tyre engineer for Pirelli and then Manor Racing. And now I write about all the engineering that goes on in the pit lane. So welcome to the seminar. We are very excited to be collaborating with SimScale. And as part of our collaboration, hopefully you will receive a special subscription offer tomorrow morning in your inbox. So make sure you look out for that. Over to you, Milad.
Thank you very much, Gemma. And as Gemma mentioned, we have this great and unique offer for everyone who registered for this webinar. And tomorrow we will send you the recording of this webinar together with a link where you can register for this offer. However, let's take a look at our today's agenda, since there are certain things we need to discuss and to understand. And just to let you know how this webinar will work. So at the beginning, we will talk a little bit, not too much, about some fundamentals. So first of all, we'll try to understand what CFD actually is and how CFD can help us to improve the performance of a race car. Followed by that, I will quickly, maybe 5 minutes, talk about SimScale. SimScale is our web and cloud-based simulation platform, which actually gives everybody access to simulation for free. And we will just discuss with you how you can use SimScale and how to connect SimScale with your own infrastructure, for example, the CAD system you're using. And then we have prepared a very nice live demonstration. This is a case study from a real-world customer, a motorsport team from the US, using SimScale to improve and develop the aerodynamics of the car, and they agreed that we can share the results with you. So we will take a look at the CFD analysis of a NASCAR, and based on this example, I will show you which kind of information we can get out of the CFD simulation. And finally, as I mentioned, we have a Q&A session. So in the case you have a question related to the content of this webinar, or maybe a general question related to motorsport engineering you would like to ask Gemma, just drop it into the question toolbox, and we will try to answer the questions on the fly or latest during the Q&A. All right, so let's dive into our today's topic, and now let's try to understand what are the benefits of simulation. And first of all, I would like to make sure that everybody has the same understanding about engineering simulation and what engineering simulation actually is. So, you know, there are hundreds of ways to explain what CFD is or engineering simulation if you want to talk about a more general term. However, I like this example very much. So let's take a look at the left side of the slide. And to understand what is the difference between a simulation, let's try to understand first what is the difference between a numerical model and analytical model. So in engineering, we have these two kind of models which we can use to calculate something or to create models for certain applications. And whenever it comes to analytical models, we're talking about models which have a closed mathematical solution for the entire domain of the model. And that sounds very complex, but in the end, the meaning of this sentence is very easy. If, let's say, you are considering or you are taking a look at the linear spring, and you want to describe this linear spring, you can use analytical model. In this case, our analytical model is F equals C multiplied with the elongation of our spring. And closed means in this case that for every point, for the infinite number of points of our domain we're considering, in this case different delta L's, for every of these points we have a unique solution, or we have a solution at least. And the great thing about this kind of model is that it's very easy to work with them. But when it comes to more complex, let's say, real-world problems, usually you cannot really apply these models, or you're not able to solve them. This is a very simple example with the equation, but when it comes to, let's say, real-world problems, for example, the flow around a race car, it's not anymore a linear equation or linear. It's for example, a differential equation, second order, and then we cannot solve it. And therefore, engineers 200 years ago started to introduce numerical models. And these numerical models are based on these analytical models, but instead on calculating an analytical solution, they are approximating the solution using defined support points and approximations between them. And this allows us to solve or calculate even complex issues. But for this, we need appropriate models and algorithms. And this is CFD. So CFD is actually the idea that we take the Navier-Stokes equation, which is the equation describing the motion of a fluid substance. And since we cannot solve this equation analytically, we are using numerical methods to solve it. And the great thing about CFD is that it's a kind of virtual wind tunnel for us. So it allows us to actually test the aerodynamic of a race car without having the need to use a wind tunnel and create or to manufacture a wind tunnel model. And so using CFD allows us to test design correctness and efficiency at the very early very early stage of the design process. And if you think about it, if you usually do a wind tunnel test, it's not only that you need a lot of money to pay for the wind tunnel to build the model, it also takes you a lot of time. And in theory, it's just a question of hours to if you want to get the CFD results from an existing CAD model. So you're saving a lot of time, which allows you to have much shorter design cycles. But it's not only that it allows you to reduce time, it also minimizes the risk of failure. Because usually when you use wind tunnel tests, as it's so expensive and it takes so much time to prepare it, you usually are not able to test every scenario. And a lot of times, we engineers, we use assumptions to build something. And sometimes it came out that this assumption we used in this certain case are not applicable. And there CFD is really a great tool because it gives us feedback about how our design will work very quickly. And finally, and now in motorsport, that's a very big point, a lot of times it reduces costs. Because a lot of time you can really replace physical testing with CFD. Not in every case, but a lot of times. And usually, let's say, a workflow which is used in motorsport is let's for example, that you want to design a new front wing. Then you start first of all just to simulate the profiles and find out of 50 profiles, which 10 profiles are working the best. Then you do maybe 10. For this 10 profiles, you do 3D CFD of the full car with the wing, and then the 3 best design ideas are tested in the wind tunnel. All right, and from what I've told you, you must think simulation is super cool. And I'm quite sure that you also hear that CFD is used massively for more than 20 years in F1, but also in other big racing series like World Endurance Championship or World Rally Championship. However, besides that, the adoption of simulation in the industry in general, and also in more particular in motorsport, is still quite low. Only around 5% of engineers have access to simulation tools. And back then, 5 years ago, when SimScale was founded, we asked ourselves, what needs to happen that simulation becomes really a standard tool which can be used by every engineer and designer. And back then we identified several reasons why people are not using simulation. And in the end of the day, you can summarize them to 3 main reasons. The first reason is that CFD is associated with a big upfront investment. So usually if you want to get started with CFD, you need to buy a software license for a CFD code, which can cost you around, I don't know, maybe as much as a Formula 3 monocoque or even more. You need to buy dedicated hardware. So usually it's really a hard case, especially for small companies, because they need to invest like 100,000 euros in advance. And another problem besides this is what we call accessibility. Even if you have access to the hardware and the software, usually you need, or it's a lot of work to build up the infrastructure you want to use, because there are different computer types you use for creating the mesh, there are different computers you use for visualizing the results, and building and maintaining this infrastructure usually is a lot of work, and it's too much work for a small company. And finally, most of the CFD and simulation tools back then were designed for simulation experts, but not for designers. And so back then we had the idea to how we can tackle this problem. And our solution was to bring up the very first web and cloud-based simulation platform. And this means that to simulate with SimScale, you only need a standard computer with a standard web browser and a working internet connection. And going on SimScale.com, you can log in on the SimScale platform and set up, run, and analyze fully flat 3D engineering simulation through your web browser. And this is really a big thing, because in the past people were limited and were forced to use what we call on-premise simulation solution. And with SimScale, you can simulate from everywhere you want. And there are a lot of things about SimScale which I like, but maybe let's just talk about the most important things which are important in the case you are working in a small race team, in a small engineering company, and you're thinking about starting with simulation. First of all, SimScale is an all-in-one tool, which means there is no hassle with different licenses or modules. So SimScale comes with the same features for all the users, and you don't need to buy a special license if you want to do a structural simulation or fluid dynamic simulation. It's all in one. The next very important point is SimScale is super fast and easy. So for a new user to get started with SimScale, it actually takes them 5 minutes to set up his account and to get started. And besides this, using the cloud technology gives a massive push to the computational power of our systems, because you are not limited anymore by your own local hardware, and you are very flexible in using as many cores and as many processors you want to get the simulation results in the time you need it. And another consequence of our cloud-based approach is that we have real-time support. So you can reach out to the SimScale team by chat, phone, and email. And besides support, we also offer consultancy as well as free webinars and trainings. And something which I think is very important in motorsport. SimScale comes with enhanced collaboration. So since it's cloud-based, you never need to make some thoughts where to save my data, how to organize my data, and how to work together with colleagues. And what I like really the most about SimScale is actually for free. So we come up with a very interesting freemium pricing model, and actually everybody can use all the simulation features of SimScale for free, but as long as you go for a free plan, your simulation projects will become public so that they can be used as templates for other users. However, I've talked for 10 minutes now about the fundamentals of CFD and about SimScale, and now let's try to take a look at the real-world example and to understand how CFD can be used to optimize the aerodynamics of a race car. If you have a question related to my presentation, don't be shy, feel free to put it into our question box, and I will try to answer all the questions as fast as I can. All right, so how to get started. As I mentioned, SimScale is a CAD or a web-based simulation platform, and everything we do it in the web browser. And today our aim is to run external CFD analysis of a NASCAR. In this case, it's based on the Ford Mustang. And usually we have 3 steps whenever we use simulation, and when we work with SimScale, SimScale will guide us through these 3 steps. The very first step is what we call CAD import. So for a CFD simulation, you need a CAD model of the car you want to simulate. And SimScale has some minor CAD functionalities to clean up a model, but we really recommend to prepare your model in your CAD system, since you will have the most control over your models there. And usually what you need to do, if you want to run a simulation of your CAD model, you need to make sure that the model is watertight and closed. Sorry. It's actually quite cold here in Germany. However, the great thing about SimScale is that it uses a measure called SnapPX, for example, which is very robust regarding problems with your geometry. But as I mentioned, try to make your model as clean as possible in your CAD system. Then you upload your model, and the next step you need to do is what we call meshing. And as I mentioned at the beginning of my presentation, the idea of numerical simulations, or of CFD, which is a numerical tool, is that instead of calculating a closed solution for every point every point around our car, that we are only approximating the flow field around the car. And therefore we need to discretize our domain into 3-dimensional cells. And this process is called meshing. And as fine as the cells are, as higher is the resolution of our simulation. So the aim of the meshing is to adapt or to create the mesh. And there you should follow the concept of as many as necessary, as less as possible. So the perfect mesh will resolve all gradients where necessary and will be very coarse wherever possible. And once you've created the mesh, and this can be a very computing intensive part, you're going to set up a simulation, explain like where's the inlet of a wind tunnel, where's the outlet, and then you can run the simulation and visualize the results in your web browser or download them for further post-processing. We got some questions related to that. So the first question is by Todd. And Todd wants to know how much memory and CPU are available for each user. Todd, that's a very good question. Actually, the computing power is unlimited at SimScale, so you can use as many CPUs and processors as you want. However, for a single simulation, the maximum number of processors you can use is 96, and this corresponds to memory around several hundred gigabytes. So, and Manjit has a question. How to manage the mesh metric at the tire and the road interface. From experience, I find it difficult to manage this area. Manji, that's a very good question, and I will try to explain it during the Q&A, since it can take some minutes to explain what's the best way. All right, and Enrico asked about the pricing model. So is the software free to use at a certain extent? Yes, Enrico, actually you can use all the SimScale features completely for free, but all the free users, they contribute the project to what we call our public project library. And this is maybe something I should show you right now, because this is one of the things I like the most about SimScale. So let's go on simscale.com, switch again to full screen, and this is the SimScale webpage, right? So, and if you go, first of all, if you go on pricing, you can see our pricing model. And we have this free community account where you can do unlimited number of projects. You can do 3,000 core hours a year, but we will extend this core hours in the case you need more. And there you can use 16 computing cores. And then we have the professional and the enterprise plans, which are not free, but there we are with our sales team will give you individual price, and there you can use up to 96 cores And so that's the difference in the pricing. But we have a lot of free users using our community plan, for example, for Formula Student or some other optimization projects. And I mentioned this public project library several times, and here it is. So it's a library consisting several 100,000 simulation projects, which you can import to your workspace with one click. And for example, if you're interested, let's say, in a car, just kind of get all the simulation, including a Formula Student car, you know, a sport car, F1 car. But it's not only limited to external aerodynamics. So, for example, if we look for fuel, we can also find fuel sloshing simulations, which can be very important, by the way, also for vehicle dynamics. Or if we look for race, for example, what will we find? Yeah, a lot of other simulations. However, it seems like we have some more questions. Let me try to answer them. Mohammed wants to know, what is the difference between SimScale and ANSYS? Well, let's make this a little bit more general, Mohammed. So let's talk about what is the difference between SimScale as a cloud-based tool and any other on-premise solution like ANSYS, Star CCM, or some others. The main difference is that SimScale is actually not a piece of software you're going to download and install, but SimScale is a web-based ecosystem where you can run simulations. And you don't need to take care for where the software comes from, where the hardware comes from. You just access simulation as a service through your web browser. And regarding the accuracy or the main technology, SimScale as well as ANSYS are using the finite volume method for CFD. So it's the same equations, the same models, just coded a little bit different. And just for you to let you know, SimScale itself uses several simulation tools in the background. One of them is OpenFOAM, which you might know, and OpenFOAM is also used by some F1 teams like Mercedes or Sauber. And but in the future we will also release some other solvers. For example, Pacefish, which is not available now, but which will be available in the next couple of months. And with Pacefish, we will completely remove the need to create a mesh. So keep tuned regarding this. And as I mentioned, because that's the next question by Enrico, SimScale just has some minor CAD modeling features, so you can scale something or split faces. But when it comes, if you want to do more of geometry cleanup, I also suggest to use your own CAD system or a free online CAD system like OnShape. Yes, since it was asked again regarding the solvers, Bhavin asked again. So we use third-party solvers, but some of them are made exclusive for us. For example, OpenFOAM, it's publicly available, and we modify it a little bit, but we also have own dedicated solver, which will be which are used for other disciplines. Then Adam wants to know about the scalability of SimScale. So it's on 96 cores roughly 100 times quicker than one core. Adam, that's a good question. In theory, yes. And especially the tools we are used, they are parallelized in a very good way. So actually it should scale very good. The only constraint here is if your problem is too small, too simple, maybe you will see a big acceleration, but as long as the model is big, it should be linear. Then John wants to know regarding if we have this special pricing for students or educational persons. Yes, John, for sure. So actually, as I mentioned, with first of all students and all the hobbyists can use our free community plan. But in addition, we also have a special plan for formal student teams and lecturers where you get the professional features for free. But for this, you need to apply, and therefore, please check the academic program page of SimScale. Frankie wants to know if we need to define the wind tunnel online or should we mate it at the CAD model. No, Frankie, there is no need to define the wind tunnel in your CAD model. You can just define it within SimScale. All right, I see we have some more questions, but let's collect them and proceed a little bit, go ahead with the presentation, and then we can discuss them during the Q&A. So, and let's now take a quick look on how our simulation will look like. So, this is our car in green, around the car we will have a control volume or a control domain which should represent our wind tunnel or the racetrack. And then we have different patches with different boundary conditions. So the flow will enter the domain from the left side. So this face surface will be a kind of inlet. The flow will leave at the right side. So this is a kind of pressure outlet. We have a symmetry plane. Since the car is symmetric, we can make advantage of this. And we will a moving wall on the floor, since there is no relative motion between air and floor. And we have so-called no-slip walls for the side and top wall. And these are walls which are not interacting with the flow, since they would not exist in reality. And now let's take a look at the SimScale platform. And this is a similar project of a very similar car. And this is, by the way, a public project. So this is a project you can import yourself with one click. And as I mentioned, first of all, we have our CAD model here. This one was uploaded as the STL model, but you can also upload a lot of other file formats. And as you see, to make sure that everything will work, we made sure the car is closed, so the radiator grills were closed. It's really a solid body. And then we created 3 entity sets. This one, very fine, and body, to define different resolutions for the mesh. And then you have actually 2 options. You can create meshes fully automatic, so you don't need to define anything besides the size of your wind tunnel. And yeah, as I mentioned, it's fully automatic. However, usually the quality of the mesh is not perfect, and the mesh is very large because it's refining a lot. But you can also create a mesh manually. And in this case, we use Snappy X Mesh, so we use hexahedral meshing, and then you actually define the size of the wind tunnel box, and then you can define different features like refinement, for example, on the floor, which you can see here to resolve the gradients. And you can also define surface refinement and even region refinements. And once this is finished, you're going to set up the simulation by creating a new simulation, and you can select which kind of simulation you want to run. Should it be an incompressible flow simulation, a compressible flow simulation, or a structural simulation? Yeah, and then you're going to define how is my model interacting with its environment, and then finally you can analyze the results and post-process them, and that's what we are going to do now together. So we've created the simulation, and now first of all we will take a look at the pressure distribution. So these images are representing the static pressure on the surface of the car, where red represents high pressures and blue low pressures. And just to let you know, you can also for sure use other representations, like instead of the coefficients, for example. And yeah, we can see how we have high pressure areas on the front splitter, on the upper side of the rear wing. We can also see some low pressure areas like on the pillars here, or on the tires, since the tires are moving and rotating. This is also considered. And now if we use another view, we can see how, on the other hand, the front splitter is generating a low pressure area. And yeah, and now let's, first of all, and that's maybe the biggest misconception in CFD, for pressure distributions on a car is usually only telling you what is happening, but not why. And whenever it comes to CFD, the great thing is that CFD helps us to understand why something is happening. Whenever you're looking to get a idea of total forces, a wind tunnel will give you a better idea. But whenever you want to understand why the flow field is looking like it is, CFD has a lot of advantages against wind tunnel testing. And therefore, we will not take a look at the pressure distribution, but on the wall shear stress distribution, because the wall shear stress helps us to understand why the flow is streaming like it's streaming. And first of all, we see that we have a lot of friction on the front tire, and this friction could be controlled or can be controlled using this front splitter side fins. And you can really imagine like the flow is going to be directed by this fin around the front part of the car, and then it's like streaming and touching the rotating tire. And since we have high wall shear stress here, we also have this low pressure area. And we also can see that there is some turbulent structures here and there, which seems to be created by the wake of the rear tire. And so just taking a look at this picture gives us an idea about two fields of the car related to the tires where we can optimize the flow around the car. The next thing is to further visualize this, we created some streamlines, and now you can really see how things are working. So the air coming to the front of the car is splitted by the splitter, so a part of the flow is guided around the front of the car, streaming around the car, touching the rear tires, and that's where we have this high wall shear stress. And here we can also see exactly how these vortices which are created interact with the diffuser. So we have some vortices created in this area which are flowing downstream and get like accelerated by the diffuser, and we have some wake generated by the rear wings which is flowing over, let me see if I have a pointer, this part of the underfloor, and therefore creating this high wall shear stress there, which we want to reduce. In addition, we can see that we have a very big wake around the car, so we have a large recirculation zone, and actually this, let's say, wake bubble is contributing massively to our total downforce. So if we want to reduce the downforce, instead of like only taking a look on reducing wall shear stresses on the car, we should try to reduce the pressure drop behind the car. Yeah, now let's take a deeper look at some of the streamlines. So we can see that we have, at the front splitter, we have strong recirculations and flow separations effect. So this edge is really like splitting up the flow, and these structures right now, they are not really enhanced and controlled, but we can use this structure by modifying the shape of the front duct to optimize, let's say, how the flow is interacting with the rear wheel. And this is something which without in a wind tunnel is actually not possible, because a wind tunnel can help you to visualize some of the flow using smoke, or even to measure some parts of the control domain using a PIV system, but it will never give you so much information for actually nearly every point in the flow domain around your car. And one thing we could do is to use this vortices now to seal the diffuser against or from the side. So actually that's what they're doing right now. So if you take a look, we have this vortices and it's like sealing the flow here, but we could try somehow to push this wake more outside, and then to have, let's say, effectively more area for our diffuser. And another thing I love about CFD is that it allows us to easily like calculate or derivate variables from our results. And one thing we do a lot in motorsports is to visualize areas or parts of the car and how they are contributing to the total forces. In this case, we are now have colored the surface of the car by the downforce it's creating. You can calculate this by multiplying for every point of the car the pressure with the normals in x and z direction. And so gray in this case means that this part is either creating drag or downforce, red means it creates, sorry, it's not contributing to forces in x direction at all. That means gray. Red means it's creating drag, and blue means it's creating downforce. And so we can see like that the splitter is creating downforce, the rear wing is creating downforce, and that the front of, or the hood and the roof of the car are actually creating lift. Not as much lift as the wings are splitter creating downforce, but it's force into, let's say, the wrong direction. And we could think about using a part like a splitter to reduce the lift generated by the windshield frame. And if we now take a look at the same, let's say, from another perspective of the car, you can also see the difference. So in this case, both the lower and the upper surface of the splitter are blue because both sides are contributing to the downforce. You can also see like that here that this part of the tire is generating some lift, and also that actually the vortex core is creating a lot of downforce in this area of the flow. And now I would like to come back to the question, one of the questions, and just let me find my question toolbox. Here it is. So one question was how to manage the contact area between tire and road. That's a very good question. And Manjit asked that question. And one thing we usually do is we use so-called tire contact patches. So, and really it's a sign itself. So F1 teams, they have people working only on this kind of problem, optimizing this patch. But in the end of the day, let me try to sketch it. If this is our tire, and this is the road. Now let's zoom in. It will look like this, right? So we have the tires on the road, and in theory you would think that the tire and the ground are touching only on an infinite thin line. But in reality, when this comes with, and this means we have two problems. The first problem is that it will become very difficult to mesh this, just from a geometrical point of view, because then they are just touching on an infinite thin line, and it will become very hard to resolve this small angle with a tetraeder or hexaeder. But the other problem is that in reality, the tire is not looking like this. The tire gets massively deformed. So what you should do is first of all try to find out in your application, for example, if it's a, I don't know, Formula 4 car, how does the tire get deformed and how it's looking like at a high speed. And then you need to create something what we call tire contact patch, which is like connecting the floor with your tire and make sure you can mesh it. Yes, the next question is by Bavin. He wants to know if we have a queuing system for the jobs. Yes, we actually have a queuing system, but actually you don't need to really think about it, because as usually when you start a simulation job, when you submit it, 2 or 3 minutes later, it's on calculation. Okay, the next question is by Peter. Peter said that I mentioned that the model needs to be closed, and he wants if it's possible still to simulate the effects like S or F duct. Peter, again, a very good question. That's why I like doing these webinars with motorsport people, because you guys really know what you're talking about. And closed has a very special meaning in our case. Let's say if I want to simulate the flow around a sphere. So this is my inlet, this is my outlet. Closed in this case means that there should be no hole on the geometry of our sphere. But if it's open, what will happen is that the flow streams in, but it cannot leave. But what you can also do is, instead of a sphere, simulating something like this. Then the model The sphere has an opening, but the model itself is still closed because we have this inner wall. So whenever you want, for example, to do a simulation with internal flows, which is also possible, then you need to make sure that your internal channels, that they are also closed. But then it's absolutely fine. Kai wants to know if it's possible to get the link to the simulation. Yes, for sure. It's the simulation itself, or a similar simulation, or a public library. So you just go on simscale.com, public projects, and check out for Mustang. However, I will see if I can add some interesting public projects to the email, which we'll send to you in the next couple of days, which includes the recording and also the special offer from Racecar Engineering. I hope that's fine, Kai. Kevin wants to know how we are considering rotating tires and if we use the sliding mesh for that. First of all, Kevin, you're absolutely right. You need to consider the rotation of the tires, but we are not using a sliding mesh for this because this would be too much of work and too complex. Even if they're not using usual sliding meshes. What we use instead is called a moving wall boundary condition. So we're adding a boundary condition to the tires, which says that they're actually rotating. And then you just need to provide the rotation center and the rotation speed. And if we want to simulate the effect on the brake duct and what is happening inside of the rim, we can use a so-called MRF, so a multiple reference zone, which is like a zone that we draw or add to the tire, and inside the zone we will add additional momentum to model how the tires are rotating. And Kazu wants to know, when the car is turning, will the underbody vertex be disturbed? How does SimScale model this? What do you mean with turning? So the car is turning into an apex or into a corner, or what do you mean with turning? Because if you want to simulate the aerodynamics around a turning car, it's also possible with SimScale, but it becomes a little bit more complex because during turning, actually, the velocity field is changing more. So you would need to really model a corner and add a global MRF zone to the whole simulation. So if you want to do a straight line simulation, let's say that's the car. Oh, wait. Let's say you want to do a full, straight car simulation. It will look like this. So this is your car. Air is coming from here. But if you want to do a car which is turning, you need such a wind tunnel domain, which is a little bit more complex. I hope it's clear, Kaiser. And yes, some other people asked regarding rotating parts. I think we answered that. Ashworth wants to know how we can monitor boundary layer separation and recirculation. Actually, that's a very good question. So I will ask the question to the audience. How do you identify your flow separation? If you know that, you will also know how to identify it for a CFD run. So just add it to the chat as a question toolbox if you have an idea what is the criterion we can use to determine the flow separation. In the meantime, I will answer some other questions. Yes, because some people also asked, simulating this car body took around, on 96 cores, 5 to 6 hours. And Himanshu wants to know if we can calculate downforce created by rear wings only. Yes, we can do this, and I will show it to you in around 5 minutes. And a question by Gonçalo. Gonçalo wants to know, since our tool is cloud-based, how to compare it to common software regarding simulation time. Well, that's a good point. We can compare it like this. If you use 96 cores on SimScale, you would need to buy 96 cores, a 96 core machine, if you want to use another tool. So, and usually since this is very expensive, it's faster, but in theory, yes, you can also buy a lot of hardware and then run it on your own with on-premise software. Exactly, and Adam gave the exactly right answer to my question. Flow separations happens there where wall shear stress is 0, or where the pressure gradient is changing its sign. So, and Bavin also gets the same question. You are really good, guys. And that's exactly the point. If you want to visualize flow separation, you have two possibilities. One is to, let me erase my drawing first. One is to take a look where the wall shear stress, higher than 0. And another option is to take a look at the pressure field, and you have a separation wherever the pressure gradient is changing on an airfoil, for example. All right. Now, what we talked, yeah. Now let's do the same for the drag force. So now we're visualizing the parts contributing to drag, and also that. So in this case, be careful. Blue means it's creating drag, and red means it's creating a force working opposite direction of drag. So and this is just theory. So in theory, you could say that your windshield and your engine bay are reducing the drag, but that's not necessarily a true, or let's say a valid interpretation, because they're just creating this force for very small parts. However, you can see it like that. The radiator grill, since it's not considered for the simulation, it was closed, and there we will have a lot of additional drag force, which will be smaller in reality if we would simulate the flow through the engine bay. And also what we can see is that this corner needs to be redesigned, because it's creating massively drag. We have a kind of recirculation of flow separation here. And this wake behind the car, this is the reason why we have this drag area here. And if we now take a look at the floor of the car, we can see again that the separation backdrop is creating some drag, so maybe here's some optimization potential. However, in general, the underfloor is generating some downforce and contributing just a little bit to drag. And now let's take a look at the Aero force distribution. So what we did here is that we calculate the cumulative downforce coefficient, cumulative drag coefficient. And here you can see like in X direction, like how different parts of the car are creating downforce and drag. So blue is downforce, red is drag, and you can see like how the front splitter is creating some downforce, how this part which generates the vortex on the underfloor is generating some downforce, and how the rear wing is generating some downforce. And at the same time you can see how they are also generating drag. And this kind of graph, for example, not only helps you to improve aerodynamics, but also helps you to understand like how about the impact of the aerodynamics on vehicle dynamics and other stuff. And for sure, we can also calculate the center of pressure for our car, which is very important for vehicle dynamics, for example. And we can also calculate the total forces for different parts. And here you can see how many downforce and drag is created by different parts like body, front splitter, diffuser, and so on. All right, that's everything from my side. And now we have time for a Q&A. So we got some more questions. Some of them get answered. Then we have some other questions. Himanshu wants to know how much time it would take on 16 course. Well, that's a good question. In this case, I would say it should take around 6 to 7 times more than on 96 course. Byron wants to know if the data can be downloaded for post-processing. Yes, for sure. You can easily download the data for local post-processing to use open source tools like peer review, but also you can import it to commercial tools. Robert wants to know which settings are available for prism growth and if I can demonstrate them. Yes, for sure, Robert. So let's go back to the mesh creator of our model, and then we have this layer addition. We will apply the layer addition to all surface of the car. We will use 5 layers, and they should grow with 30%, and the total thickness of the final layer should be 30% from the cell height, and the minimum layer length should be limited to 1% of the local cell length. So in this case, you're defining the SimScale, you're defining the properties of your layer mesh. By defining ratios between the cell or the surface mesh on the part and how your layer mesh should look like, or your design mesh should look like. I think the mesh for this simulation considered around 20-25 million cells, but we also run simulations with several 100 million cells on SimScale. Yes. All right, it seems like all the questions are answered. If there are no more questions, I would like to thank you very much for being with us. We will send you the recording of the webinar together with the offer from Racecar Engineering and some links to some other material on our website in the next couple of days. I think tomorrow, it should be tomorrow or latest Friday. Yes, thank you very much. Also, Gemma, thank you very much for being here with us and for the great collaboration. I hope you enjoyed the webinar. I wish you a wonderful week and see you soon. And in the case you have a question, you can reach out to me by email. Bye.